I pressed the share button. Can you see the screen? Almost everything that I actually do, is going to be drawn from a. Okay, great. Never mind. All right, so I don't think we'll be here that long. I came up with basically what I did was I started writing the exam. And the reason that I started writing the exam rather than come up with a review sheet is I didn't receive any negative feedback for doing a take-home exam. On top of that, I'm actually going to be gone next Tuesday, just next Tuesday. So I'm leaving on a not just next Tuesday, but I'm leaving on a trip Saturday. I return home Wednesday. So I won't be here to actually hand out a paper exam. I mean, to hand out a course, an in-person exam anyway. So I could have found a proctor, but instead, what I'm going to do is sometime tomorrow. I was earlier today. I actually only found out about this trip. The tickets weren't bought until Thursday of last week, and I found out about the possibility of it on Wednesday. So what I'm going to do, I thought I was optimistic. I thought maybe I'll be able to write the whole exam today and just give it out right now, but I wasn't. So what we're going to do is go over the format of the exam, talk about it. If anybody has any questions, then I'll answer them. If not, then we can go, and I'll post the exam before I leave tomorrow for my Thanksgiving, which is tomorrow evening. So I'll post the exam before tomorrow evening, and you all can start working on it. And here, we'll just go to it. By the way, I've already posted this text, and that's on the course website under final exam material. And I'm actually going to post the final exam here, as well as a link to this video that I'm creating right now. By the way, that's what I'm doing, creating a video right now for the people who aren't here. There's 4 people here, which means about half the class. And then we'll go at it. All right, so this is the beginning of the exam, and we'll go over it and see if there are any questions, and then go over an example, a question that will remain on the exam. We won't actually work through it, but we'll work through working through it so you can see that. All right, so here are the instructions for the exam. Basically, we're covering chapters 9 through 18 in the book, which is almost all the chapters except for the they call it the epilogue. It's really kind of a review. Not that 9 through 18 isn't all the chapters, but 18 was the last new content chapter in the book. Chapter 9 was the one that started with hypothesis testing. So basically, almost everything that we covered, pretty much everything we covered, had you do hypothesis tests. So for this exam, you're going to be given a number of questions, and unless otherwise stated, there'll be a hypothesis test to perform. And what I want you to do is, when you encounter a hypothesis test, you're going to follow the steps that we discussed as part of Chapter 9 on classical hypothesis testing. Okay? So if you remember those tests, step 1 and step 2 were to state the null hypothesis and to find out what test you wanted to use or you were going to use. Now those steps almost happen in conjunction with each other. Sometimes you identify the test and then state the hypothesis. So although they're called step 1 and step 2, those are really similar tasks. And we're just going to follow the book as method. So you might actually do step 2 before you do step 1. That's fine. but answer them in the order that they're listed. Step 1, and then step 2. So step 1 was state the null on the alternative hypothesis. Step 2 is identify the statistical test that you're going to do. So that could be, I mean, we'll just review some of the tests where the very first one was the difference in one sample, difference in means test, where we did basically compare a sample with a population, and then we did 2 sample difference in means tests, and there were 2 varieties of 2 sample tests. There was one matched pairs, one that was not matched pairs. Then, well, actually, kind of involved in all that, we discussed difference in proportion tests, which are related, but their formula is slightly different. Okay, and then we got into ANOVA. We did ANOVA testing, and what makes you need to use an ANOVA? Well, if there's more than one group. I'm sorry, if there's more than 2 groups. So it's basically a difference in 3 or more groups, difference in 4 groups, difference in 5 groups. Those would all be ANOVA tests. Now, if it's non-parametric, then you use Kruskal-Wallis, which is another one that we discussed. I will, one of the things that you should remember, or that you should know, I didn't write this in the example, but I'll update that right now. I'll write this. Maybe I'll move the position, but I'll write this right now. Assume that you can use a otherwise. So in other words, you should assume that you should assume that the data would support you using a parametric test. In other words, that it's fairly normally distributed unless otherwise stated. Now, for some of the questions, I will supply some data. So I'll supply some data in the form of an Excel spreadsheet. So that will be there. But I'm not expecting you for any of the examples to come up with a justification as to whether you should use a non-parametric or a parametric test. You can that'll be stated whether or not you should use one or the other. Well, actually, it'll only be stated if you should use a parametric test. It might not be stated which parametric test you should use, or which non-parametric test you should use. All right. Okay, let's look at some of this other explanation. So step 1 and step 2, not always done in the order. Second thing there, unless otherwise stated, the significance level to use is 0.5 for step 3. So step 3 was identify a significance level. So unless I tell you otherwise, it's 0.5 is what you should use as the middle of the road test. All right. For step 4 was the one that said that you should identify the basically the area, you're looking for the area under the curve value that you need. Identify that threshold value. Now, sometimes you're going to be using software, and there's when you're using software, there's no need to come up with that threshold value. And so here it is sufficient to just specify whether it's single-tailed or two-tailed. You do not have to specify what the critical value is, especially if you're using some software.
When we're doing some of these, you get this what you just call it critical value. It's going to be some examples of
yeah.
Sometimes I don't know exactly what that critical value is. What is that even? What's the value?
Okay, so I'm just going to move that up there because that makes sense right after, because this is the direction for this. That line I moved up there is the direction for for which test you use. Okay. So your question was a critical value. What's good? So I mean, what's the reason?
Every test.
Right. Yeah. So you understand that for every test that we've created, you get a test statistic. The test statistic is what's compared to the critical value. And if you have a test statistic and a critical value, you really don't need to know what the p-value is, okay? Because I should have brought my my crayons today, or not crayons. I'll draw this up because it's the way it'll get recorded better anyway. All right, so if I'm doing something with a z or a t distribution, this is bad because it's on the screen. But if that looks similar to a z or a p distribution, it's got a hump in the middle. All right. So when you come up with when you do a test, like let's say you did a difference in means test, the result of that would be a z or a t statistic depending on whether you had 30 samples or fewer, whether or not you should use a t or a z statistic. But you'd get a value, and that value might be right here on the number line, because it might be something like 2.4 or something. No, so, okay. This is the test statistic. So that's the number that you get, like if it's a difference of means test, it's, mean 1 minus mean 2 divided by some combination of the standard deviation, where you have to look that up in the book, right? So you get a number. And then the ultimate goal is to find out whether or not you're accepting or rejecting the null hypothesis, right? Okay, well there's kind of two ways to approach it. One is if you're using software, you plug it in and it just spits out a p-value to you, right? And if that p-value that spits out is greater than or less than 0.5, then you know whether or not to accept or reject, right? Okay, however, before we had those abilities to have the computer spit out the p-value, in fact, what it's doing inside of its brain, the computer's brain, is it's finding out the t-value associated with, what it's actually reporting. The p-value that's reporting is the area under the curve right here. So that's horrible. The computer is reporting this value as your p-value. That's the area under the curve. Does that make sense? Okay. The test statistic. Yeah. The critical value is let's say this was 0. Let me get a different color. Let's say the area under the curve right here is 0.5. The critical value is this number. It might be 3.1. A little bit more sense. It's the number at the edge of the significance level, the p-value that you. So this is the p-value. This is the number at the edge of the. In other words, if your test statistics worked out that you were right on the edge, it would be that number. So you can compare your test statistic to the critical value. That's what the critical value is. The critical value is the number that you're comparing. So you can, another way to say this is you compare p-value to your threshold. So your significance level. You compare your p-value to your chosen significant level threshold, which unless I specify will be 0.05. You compare your test statistic to the critical value. And there's just two different ways of looking at it. One is the area under the curve, and one is the area on the, is the distance along the axis. So you can compare the distance along the axis, or you can compare the two areas under the curve. And obviously, if it's greater, it's farther away. Okay? Whereas if it's, in this case, if it's less, it's further away. If your number is less than your test statistic. So you don't really need, you don't need to have both sets of information in order to know if you reject or accept the null hypothesis. So if you're using a computer program that only reports the significance level and it's greater than 0.05, you're good. And that's why I'm not expecting you to answer both. If you know the test statistic and the critical value, you know enough. Either way, you know enough to reject or accept the null hypothesis. All right. Yeah, so that's what I meant there. Okay. For step 5, you're going to report the test statistic, and where specified, this is where you should report any other values requested in the problem. So all software packages will report the test statistic to you.
That's useful for like regression test statistic.
Yeah, so with regression, the test statistic is an F statistic. I really should have run my book, but it's the F statistic, right? And it's not super important for lots of things. The p-value tells you, the p-value and that statistic together tell you what you need to know. Now, I did say in there, where specified, this is where you should report any other values requested in the problem. So for example, with regression, I'm definitely going to request the R-square value. I'll probably also sometimes request for a regression problem the coefficients. Basically, I might ask you to, for regression, I might ask you to come up with a value using the model for another location, kind of like you did on the homework. So like, if you're regressing a value like income and education, then and you come up with, you multiply it by 10, and then your constant is 12, which is the y-intercept. And you plug those into the formula. If I say, okay, well, let's say somebody made X amount of dollars, what was their education level or whatnot? Then you plug that in using the equation. All right. Step 6. For step 6, include any requested. For step 6, include any requested discussion, as well as a formal statement of decision regarding the hypothesis. Okay. So, for example, again with regression, we might the test will definitely ask you some discussion questions. It won't just ask you whether or not the relationship is significant, because oftentimes with regression, there is a significant relationship, but it's still not it's not very powerful, or it's not very useful, depending on the R squared or depending on the standard error, like for example, the housing example we did last week. Another example where I say in test for step 5 for test statistics, another example would be in the spatial portion. You might have to interpret the given value, whether or not. So you should definitely know the different types of spatial autocorrelation. Obviously, you can go back and look at the book. So you've got dispersed, random, cluster, and know where they fall in there. Okay. All right. Now, for the next part, it says you are free to use any material or resource. So it's software, etc., whatever you want to use. you're even free to come ask me. What I will do is if somebody comes to me and asks a good question that I believe clarifies something in the test that wasn't very clear, I will post that information up on Blackboard and probably even email people out. Okay. So the only restriction here is that you should work independently. Now, when I say work independently, what I don't want to have happen is for everybody to come up with the exact same answers. That would be bad. However, there's some area where somebody might say, how were you able to do a Kruskal-Wallis test or whatever? And you might say, well, I use this software or that software. Okay, that's okay. Helping people refer to portions of the book or whatnot, that's fine. You just work separately on the on it rather than working together on it. Okay, where was I? All right, I will be away doing field work until Wednesday, December 2nd. However, I have access to email even over this period. The exam is due December 9th. So December 9th is actually 2 weeks from tomorrow. So, I realize that most people will be doing Thanksgiving and all that. I do not think, even though I'm going to post this tomorrow afternoon or evening, I don't think that you need to work on this over Thanksgiving break. Thursday, Friday, Saturday, Sunday. I don't expect you to work on it. If you wanted to work on it, that's totally fine. But the reason why I'm posting it that early is so that I don't have to worry about it when I'm traveling on the field work and when I'm at Thanksgiving. So posting it that early for those reasons. But you should be just fine with a week and a half. Maybe you'll see when you get the test that you can make a judgment as to when you need to start working on it. All right. Anything else? No, that's a good idea. I turn it in. Let's email all these in. And another thing that I was going to say before you even brought that up is that I'm not providing enough space. I'm just listing out the questions, not enough space to answer. So answer on a separate sheet of computer. You're all graduate students. You can use the copier downstairs, right?
Yeah.
Yeah. So if you do actually do your test either written out or you produce a hard copy, you can use that machine. I don't know has anybody used that machine to email? Yeah. If you use that machine, you stick it in the machine and you hit contact list, and I'm in the contact list, and so you can get the email. All right. If you did want to produce a paper copy, that's fine. All right, so here's an example of a question that I created. I created several others, but I deleted them up to now just because I didn't have a chance to proofread them and everything like that. But so this is one example, and I am going to go, just so you know, I am going to go fairly chronologically through the book when I answer the questions. So that should be a clue to you. If you're thinking I should do regression here, you're probably off because that's towards the end. Okay, so that's just another little helper. Although I don't state which test you should use, know that it's for the most part chronological. Now, in some ways, that might be a hindrance because you might be deciding whether or not this is a proportion or a means test. But if you read the question, you should be able to get that part. So suppose that a new weight loss program marketed in Mississippi claims that participants lose at least 5 pounds by participating in the program. So you randomly sample 40 people on the program within the state in order to validate the claim. You find that their average weight loss was 4 pounds with a standard deviation of 0.5 pounds. That's the validity of the claim. Anybody have any, so this is an example of where this is going to remain on the test, but it's fine right now to discuss this, and I'll work through it. Anybody have any, for step 1, what are we testing?
Your null hypothesis, is that the word? Or we're not doing it?
Yeah, the step 1 is finding out the null hypothesis. We can do that first, or you can figure out what test you're going to do first. But the step 1, the one you're going to have to write is null hypothesis first. Okay? Right, exactly. So there's no significant difference between this mean of 4 and the claim of 5 pounds, okay? All right. What test would we use? That's actually good. I mean, you want to write that out a little more formally like the book, but it's right on. Okay, so what test would we perform here? Is this a 2-sampled or single sample, or yeah, it's a difference in means. Do we have, is it a 2-sample or a single sample test? What's that? You're right. Single sample.
And comparing one sample to what claim.
To what everybody claims, right? Now, technically, the way we introduced it in the book, it was you're comparing a single sample to a population. But in this case, we're comparing our single sample to an unknown population, which is okay. We don't actually have the information for this population, and that's actually the way it often is. If we had the information for the population, we wouldn't really need to do a test. We'd say, oh, they're different. Okay, so yes, this is our population. Our population is all those people participating in the program, and although we don't know if their weight loss really is 5, we're comparing it to see if our sample could have been drawn from a population where that was true, okay? So we randomly sampled 40 people on the program within a state in order to validate the claim. You find that the average weight loss was 4 pounds with a standard deviation of 0.75 pounds. Test the validity of the claim. Yes, so now that we've established that, it's really just mechanics of working through it. The only other thing to really be decided here is whether or not this is a 1-tailed or a 2-tailed test. Okay? What do y'all think as to whether or not this is a 1 or 2-tailed test? Yeah. It's either significant or not significant. Yeah, I mean, the test is significant or not significant. I think you're right at the 1-tailed. The 1-tailed. Yeah, exactly. So the word "at least" in there helps you to indicate that it's a one-tailed test. And so you need to make sure that when you do that, your null hypothesis and your alternative hypothesis are stated like that. So yes, the test here is at least means that it could be 5, it could be 6, it could be 7, but it's going to be at least 5. So it's a single-tailed, which is if they said something like that, it would be 2-tailed. However, it would be hard to test without knowing what the reported mean is. So, so in that situation, it would be hard to use any of the tests that we discussed in class. You have to say, well, what's the mean there? But what if they said that the average weight loss, the claims was 5 pounds? Then you would use 2 grams.
So it's 5 pounds you're testing at 5. It falls close enough to that 4 mean, and within 90%.
Right.
Nothing.
Yep. And well, we're doing a 95% confidence interval. It's not specified. And you actually could get the answer that way. Like if you went back to chapter 8 and you just built a confidence interval about this mean, about the 4. Okay. You build a 95% confidence interval, or in our case, yeah, 95% confidence interval. Yeah. Now remember, it's one-tailed, so it's really not just a 95% confidence interval. You have to go a little bit further than that. One-tailed, so it's, you also have to cut half of the 0.5 to get that value. But you built that and you noticed that 5 was within that confidence interval, it would test it. But that'd be a convoluted way to do it now that you know about hypothesis.
You already have the average weight loss score. Claim influence is at least 5. So that's like, that's the majority of people are claiming to be at least 5.
No, this is what you'd say is the population mean. So what you're saying is the population should be 5. Population mean should be 5. At least 5. These people have had a weight loss where they lost 4 pounds with a standard deviation of 0.75 pounds. Is it possible that these 40 people could have been drawn from this unknown population? Could I have? Is this within the possible state? Possible sampling error.
You just find out how many standard deviations 5 is away from 4, and that's your t-score, and then you have to put it back to
Yep. Yeah, that's just a matter of going through the mechanics. Okay. The formula, I'm pretty sure I remember this, is the sample mean minus the population mean divided by the standard deviation. And then there's some combination of, you guys have the formula, some combination of you need the n. I know you need the n.
It's not like you want to observe and
This one will be chapter what?
I think it's in chapter 9, page 149.
Yeah. Sample mean divided by
That is, so it's the standard deviation divided by n, the square root of n, or if you got less than 30, it's the square root of n minus 1. It's 1.92. I'm sure that Google will. Now we've established this is a one sample test. Yeah.
I remember reading somewhere that you're supposed to, in the book, the difference between one of them is that you use your population has to be greater than your population. Sample size is greater than 30.
Mm-hmm.
Also mentioned something about if I think it was the standard deviation of the population, even if your sample size is greater than guides for the determinant of the subsystem variances?
Okay, so you need to be careful on which hypothesis test you use. So some hypothesis tests, the rule is 30 and greater, which is the case with the 1 and 2 sample difference in means test. But some of the proportion tests, you use a different rule or don't even, some just don't even, some of the tests only use a t-statistic. Just follow what it says in the book.
I think that came from like you do the standard deviation.
Right.
Regulation. I think.
Yeah, that's true.
But you have the standard deviation.
Well, I don't have the population standard deviation.
Yeah.
Oh, so you're asking. Sorry, I don't have a book on me.
I don't know what that is. I remember it. I got it.
Yeah, so with this one, with the one sample difference of t-test, the rule is the cutoff. Okay, the rule is if it has 30 or less, use that. See if I can find another one in here. So the proportions, one sample is the same way, two samples the same way, which is what I said, so not inconsistent so far.
Two sample difference. It says sample sizes are greater than 30 and population variances are known.
Oh, okay.
And if they're unknown, or if they're less than 30 and unknown, use T.
Yeah, I see it.
So if you don't know the population variances, but you have over 30.
Yeah, so it says and. So this is a good question, Heather. So if sample size is less than 30 and population variances are unknown, use T. If the sample size is greater, so yeah, it leaves out. I see what you're saying because it uses and in both statements, right? Yeah. You have to use the degrees of freedom when you use these. Yeah. Yeah, so in this case, the answer to the question that Heather originally asked is to use Z, we're going to go with both of those being true, the and. The sample size has to be greater than 30, greater than or equal to 30, and the population variances are known. And then the next one should read, if the sample size is less than 30 or the population variances are unknown, use T. That would get every scenario. All right, but this doesn't apply to that because that's two samples. This is one sample comparing to a population. So the only thing that you need to check here is if this is greater than 30. Go ahead, sorry. It would be Z on number one, that's correct.
As in the paragraph, it says most geographic applications of the two samples of different tests the variances of populations are not known, and therefore the test of this C cannot be used.
Yep. Yeah. I was always taught that, and so that's why I corrected that statement. Yeah. So The second statement there should have the word or in it. Not an and, because two ands make it so that there's still one more possibility that you have more than 30, but you don't know the variances exactly. All right. Okay, so anybody have any other questions at this point? Yeah, go ahead. Okay. Yeah. Yeah. Yeah, well, I think we did that in class once. So the question is it possible to calculate a chi-square, like chi-square goodness of fit? Yeah. I'll show you what that is. That's what's that? It is possible. I don't know why this is taking. Yeah. And there will be some cases where I'll just say, this is the test you're going to do. Okay. So, what chapter was that? I don't know, because this is not meant for that. Okay. It's, what is it under? Yeah, legacy dialogues. Chi-square, right there. And so I don't know if this data will work. Yeah, this data won't work for that. But if you had data that would work better in it, yeah. So we demonstrated this in class, but that's a chi-square test right there.
The same problem I did.
Yes. Oh yeah, you asked me. So the question here from Michael is, he came to me and asked if you could use percentages in a chi-square test rather than using the raw counts. I at the time I said I don't know. I'll have to check that out, and I didn't ever get to that. But it's meant. I know that the chi-square is meant to examine the distribution. So you're looking, for the most part, you're looking at the actual numbers rather than the percentages.
If there's just a relation of the numbers, and it doesn't matter.
Right.
The numbers still in the room. If you're involved outside of the
Right. Yeah, that's something that I'll still have to investigate. Mm-hmm. Yeah, I guess like what he's asking is, let's say that we're looking to see whether or not test grades over a 5-year period are changing. And so if you just have the number of people that passed each year versus if you just have the percentage of people that passed each year, are those any different? That's basically what you're asking. I don't think there should be any problem with it, but I did not test. Yeah. Because you're looking at you're looking to see if the distribution, you're comparing it to something. So if you're saying, 75% should pass, and you have that value, and you're looking at the percentage changes over years, that should be the same as looking at the actual numbers over the years. Go ahead.
Yeah.
Okay.
You go again on this down. Yeah. Another test.
Yeah. Okay. So the question here is for analysis of variance. The F statistic for analysis of variance. The test statistic for analysis of variance is the F statistic, and the statistic is calculated by the ratio of the within group. The within group is the denominator. That's right. So within the within group mean squared is the denominator. The top one is between group. That's right. So it's the between group variability divided by the within group variability. And so how do you get the test? That's how you get the test statistic. You're free to use software to calculate those values because they're not easy to calculate. But then let's say if we wanted to compare that value to a critical value that we got, and most software will actually tell you the value that you want to use. So if you went to the yeah, I would use SPSS for that. I mean, in practice, usually I'm trying to calculate a bunch of things, and so I program it. But yeah, you could use that. Contingency tables. So here is the one-way ANOVA thing. And so what you do here is you would have a number of values. Like actually, we can change these here. All right, so I have basically three groups of data. So I have three groups of data. I've labeled them 1, 2, and 3. They're three groups. Some of the secret to using SPSS is figuring out how to use the software with the data you have and getting the data into the right format. By the way, those are types of questions that you're free to ask each other how to do. So like if somebody says, hey, I get my data working in ANOVA, you can ask them. You can also ask me. I'll help you do that. Okay. All right, so here we go, analysis, and go to, where was it? Compare means, ANOVA, and our we're going to put yield in the dependent list, and we're going to put variable 00001 in the factor list. The factor is the group, basically. So if we hit OK, it runs through, and it gives us an F statistic, and it gives us a significance level. So is this significant? No, it's not significant. Yeah, so there's really two different, this is what I was explaining before. There's the cutoff value, which in our case is 0.05, because that's what we said it was going to be. And then there's this value. So yeah, this is another way to say p value. All right. Now, let's say that this wasn't reported. Okay, so going back to your original question, the degrees of freedom here is 2. Why is it 2? The 3 groups, and so it's 1 minus the number of groups. And so if we go to, yeah, it is a 3 group degree spread, but it's the one that you need to use for this test. If you go back to the tables here, with degrees of freedom 2, and then degrees of freedom 1, which is 36. That's this one. The critical value it's not even on here, but you can kind of interpolate. The 30 and 40 are both on there. Well, actually, they're both 2.9, so it doesn't really matter. If you look at 2, and then between 30 and 40 they're both 3.3. So 3.3 and 1.55. Let's go back to here. I know this isn't the same curve as the F statistic curve. The F curve doesn't look like this. But if this was, what do we get? 1.6? What's the number that we got? Just got. So 3.3 is beyond that. So do we accept or reject? The test statistic is 3. Oh yeah, 1.6 I think. And this is 3.3. The critical value is 2.3 that I just looked up in the table. 2, and then 30. Right. So they're what do you call it? You're not rejecting them, so they're not significantly different from each other. And we could have gotten that same information by just looking at this one. That value is greater than 0. So this is the area under that curve. The value 3.3 is telling you the area, the distance along the line where you only have 0.5 left under the curve.
If the value was significant, you can say at least one group is different.
Yes, exactly. At least one of the groups is different. That's exactly what you'd say. Not that they're all different from each other, but at least one of the groups is different. All right. Good. Contingency tables. I think we did talk about that. It's not going to be in here. Because there was the contingency analysis that we talked about. Where did that go? I thought we did try it out. No. If anybody remembers, let me know. I hadn't actually made a question about contingency, but those are good. It's a good one. I'm sure that, I'm not sure, but. I'm gonna watch a whole video for that. Where is it? What's that? Yeah, I'm just trying to figure out how to do it in, because I know we even demonstrated in class. Data, weight classes, descriptive statistics, crosstab. That's where it is. There it is, crosstabs. That's what you would do. So to get the chi-square contingency analysis, you probably even want to check the contingency coefficient here to get it, and then you'd interpret it like they're saying here. So your initial data would have every observation, and then it would have your other observations here. You could just have, two, but you could have other factors. Like you could have, like the example in the book, it wasn't an example of the book, but you could have a number of different values where at least one was numerical, and then you had a number of different categories. So you're looking at, what's the likelihood that somebody would vote a certain way when they have some other characteristics. Yeah, so like from the book, variables are organized by nominal or ordinal categories. That means that the nominal or ordinal categories mean something like, Republican or Democrat, or maybe high, medium, and low income levels, or something like that. They fit into categories. Just like the regular ANOVA test, you have one category and then one variable that you're testing. Right? That's how you do an ANOVA test. Okay. With a contingency analysis, you're basically having multiple categories, and your categories. What's the book one? Low and high obesity rates and metro and non-metro areas was one of the examples in the book. Okay? So you're testing whether or not there's any interaction between those two categories. So the hypothesis, there's no relationship between the two variables in the population from which the sample has been drawn. There is a relationship. In other words, it's kind of like, I think I made this comparison in class, didn't I not? It's kind of like regression for two categorical variables, two or more categorical variables. most of the examples we'd be given are 2, and I won't do anything besides 2 on the test if I do put a question. I can do an example real quick. Do an example. All right, so cancel out of this, cancel out of that. I'm just going to clear all this. Let's say I have high. Actually, SPSS is really picky about using numbers. I'm just going to use numbers. So 1 means high, 2 means. Yeah. 1, 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3. So I have three income groups: high, medium, low income groups, and then I basically have 2 different voting patterns. So I got people that are voting Republican and people that are voting Democrat. Oops. I could have also put independent in there, but I'm not going to. All right, so those are my 2 groups. Let's go and say, now we are violating some of the things with the amount of samples that we have, but we're still going to run this. So we go to analyze descriptive statistics, cross tabs, and we choose 1 for one and 1 for the other. It doesn't really matter which one. Statistics, chi-square. I'm not going to put correlations because it's going to return that. Say okay. Say okay. There's the result. So this is just a raw cross tabulation. So maybe this is Republicans, maybe that's Democrats. So maybe this is high, medium, and low. Or sorry, yeah, let's just do low, medium, high income levels. So this is the raw numerical count. Total people that we have is 14. And here's the chi-square test. Here's the test statistic of degrees of freedom, whether or not it was significant. This is like way close to the middle of the distribution. That's obviously not significant. So those are not, it's not significant. So that's saying that there is no interaction between those 2 values. I could just rerun this real quick. Okay. Now look, all I did was make it so that all the ones fell in the lower income groups, and the 5 fell in the higher income group, and now all of a sudden it's significant. Not all of a sudden it's significant. The value is 14, way over there. So that's a contingency analysis in SPSS. All right. Any other questions?
Say you run the last one, we're in regression stuff. I just want to get a better understanding of like when you get all these results here, what were they? So it asks, write down the standard error, what's the test statistic, coefficient of information. So, like, what does all that mean? And because they have some like application stuff, I wonder what it means.
Okay. So in all of these questions, it asks for pretty much the same things, right? It asks for, I'm just looking at the beginning of one question. So it asks for the slope and the intercept, the slope and the intercept with the multiple regressions, it might ask for the constant and all of the coefficients. Yeah, that's basically the same thing. That information is necessary for reconstructing the equation. That's what that's for. Okay, either the slope and the intercept or the constant and all the coefficients. That's what that's for. The explained and the unexplained variance is not directly useful except for the explained and unexplained variance. The ratio of those values is your R squared. And that's a little bit more useful because that's standardized. That's always going to be a number between 0 and 1. And the closer it is to 1, the more explained variance there is because it's a ratio of the explained variance to the total variance. And so, yeah, that's what I'm saying. Yeah. I might have said the wrong thing. I might have said it wrong, but it's a ratio of your explained variance. It's all recorded, so you can go back and email me and tell me I said it wrong if you want. All right, so then you've got your what are the values of explained and unexplained variance. You should be able to calculate that. Yeah, okay. So sometimes it calls it R squared, and sometimes it calls it a coefficient of variation of determination. Those are the same values. So that's your ratio. So like I noticed, it doesn't ask you to do this, but if you took this value here, the explained variance, and you divide it by the unexplained variance, you'd get a value really close to what you calculated. All right. So, you know, it kind of depends on the question you're answering, but in general, if that value is really low, like 0 to 20%, it's not explaining very much of the variance. Even if it's statistically significant, it's not really explaining much of your variance, and that will bear itself out in your standard error. Okay. If it's in the, you know, if it's right around 50%, it's marginal. If it's up above 60%, it's marginally strong. If it gets above 80%, it's pretty strong. Okay? Pretty strong relationship. Now the standard error, that tells you, basically that's kind of like the equivalent of the standard deviation. And if you were just looking at one variable, the standard deviation gives you an idea of how much spread there is, right? So the standard error of the estimate there means that when you make an estimate using the equation that you just got, that gives you kind of an error band around that. Yeah, exactly.
So if that's really high, I mean, usually our
right, they are related.
Yeah. You're not gonna
There are situations where 2R squareds, even for the same set of data, not the exact same set of data, but if your data had a bunch of variability, but the variability was different in its characteristics, like in other words, most of them were right by the line, but there was one that was really way off, that could give you a different standard error, even if it gave you the same coefficient of determination.
But normally if you compress here,
Yeah,
so
it could.
do we decrease that?
Yeah, generally, the further your points away on average are, the greater the lower your coefficient of determination and the higher your standard error would be. All right. The higher your standard error, the lower. So both of those measurements, particularly the standard error of the estimate, really tell you how powerful your regression equation is. How predictive is it? Even if it's significant, you know, if you're trying to predict home values and you're within $200,000, it's not as useful, right? Even if it's significant. Now, if you're trying to report something like the strength of the relationship, it might still be significant to report that. You know, if that was 50 or 60%, you could still say, well, we've explained lots of the variance, although the model isn't. I wouldn't say lots of them. Over half the variance, the model isn't. Okay, the test statistic for R squared and the p-value. So the test statistic is just the F in this case, and then the p-value also reported.
And when you do that, there's an equation for it. It has R squared minus or times whatever. You don't take R squared and square it. You just use the R squared out. You know what I'm saying? Like, for the test statistic, it says for this one, the test statistic. Take R squared and square R squared.
No, that's R squared. That's R squared times n minus 2 divided by 1 minus R squared. That, if you want to manually calculate, yeah, that's actually pretty easy to calculate. And then
You don't square it.
you still have to tell the degree of 3 in order to do that. You can look at the value on the table. And most of the time that'll be in. Most of the time that'll be in the. When we do regression. Yeah. Like since these values are numbers, I could actually do regression, linear, and okay. So here is the significance value. Here's the F statistic. Here's the correlation, the R squared, the coefficient of determination. Sorry, this is actually the correlation coefficient. Back when we talked about correlation. So that's R. This is R squared. That's pretty high value. Remember, we're just dealing with 14 numbers. Standard error of the estimate is 0.43, and we're talking about 1s, 2s, and 3s. So it's still pretty high, but it's
More samples might help that. Maybe.
what I'm trying to say is it's made of values, so it's not really that important. That's that. So those are all the numbers that you report. So this number, that number would all be important numbers. All right. Oh, and this is the unexplained. The explained variance. This is the total variance. The total sum of squares and the unexplained sum of squares. Divide this by that and you get this value. You can see that this is about 75% of that number. All right, any other questions?
Calculate have at the top like the sum of the nearest neighbor value.
Mm-hmm.
If you were just to count them down, I mean, logically, we have like 40 B and there's 2 other points next to it. We're trying to figure out, you can't just add up the distance. You have to pick the one that's closest. You have to go through each one of them. when I was working with the homework day, I had confused with some of the nearest, or you pick the one that's nearest, right?
Yeah.
You can't just, because when it says sum, I'm just assuming I can just add them all up, but you can't just add them just
The sum of all the nearest neighbor distances would be the sum. Right, it's always the nearest. Yeah, the connections are always to the nearest one.
It seems like it should make sense.
Yeah, no problem. All right. Cool. Well, if anybody has additional questions, let me know, and I'll post the test up, and this this will be due. I already said when it's due, the 9th. So what do I mean by the 9th? Somebody's going to ask that, right? I'm fine with midnight on the, I guess 11:59 to make it more clear. 11:59 p.m. on the 9th would be the moment before it turns into the 10th. What's that? Which year? Yeah, somebody could say what time zone, but we're gonna stick with Central Time. Yeah, I just had to. I was supposed to turn something in. Then they said 11:59. Supposed to turn something in, and I turned it in at 11:59 Eastern, and they wanted it at 11:59. Sorry, I turned it at 11:59 Central. They wanted 11:59 Eastern, so I was like 30 minutes late because I turned it in. I was doing it a little bit early this week. They were fine. They didn't freak out or anything. It was just an article, a research article that they wanted us to reformat everything.
So they got right on it.
Yeah. Yep, exactly. So you probably realize that if you were up really, really late, you don't need to freak out. You could still turn it in. I'm gonna say 11:59 is the deadline, but you know that I'm not gonna wake up till 8, and I'm not really gonna care. Well, not wake up. I'm not gonna sit in front of my computer till 8. All right. Any other questions? Hopefully, everything. I guess Heather, this means you don't have to drive up anymore, unless you need to do it for another class. Oh, okay. That's right. Okay, sounds good. No problem. I'm gonna go ahead and hang up then. You too. Or